Okay, so we saw earlier that we didn't have any control parameters when I ran the patch. So there's nothing I can do. I can only hear the oscillator output because we created an oscillator and we connected it to the output. Let's start with deleting this oscillator because we will make our own oscillator. And let's begin by making some input controls. So we can make something called an input event. It has the float data type. We would like to set the carrier frequency like this. We also need to annotate this with a name. Let's call it carrier frequency. And we need to set a minimum value. Let's just set 0.5, a maximum value. Let's just say 100, an initial value of 0.5. The units will be hertz. So when I run the patch, output stream. So I need to close this. When I'm running the patch, now I have a dial that works like this. You can see it has a minimum of 0.5, a maximum of 100, and it initializes to the value of 0.5 like this. And the units is actually not written anywhere, so I don't know why to write that. Similar to MSP, where we can create like objects like this, we can also define something called a processor. If we want to make our own oscillator, then we can make an oscillator processor like this. And the processor should also take an input event float, and we just call it carrier frequency. We need to make at least one output, so we just make an output stream float, audio output. Okay, so the difference between this input event up here and this one is like this input event comes from somewhere outside CMajor, right? Events from outside CMajor enter through this input event. This could be from if it was running on our website or an embedded system or something. We can then connect this event to the input event of our processor. If we make, let's say we make a oscillator, and that's a new oscillator like this. And in our connection, we would like to connect our carrier frequency to the oscillator.carrier frequency like this, right? So that means any events which are float, which are entering our main graph, is transmitted to this instance of our oscillator processor, and it's transmitting the carrier frequency to the input event of the oscillator. So this instance of the oscillator processor is now connected here. Okay, when I'm moving my dial, I change the value. We saw that before. But the problem is that I can jump like quite rapidly. And if I set my carrier frequency without any ramp or any smoothing, then it will sound pretty awful. There will be a lot of clicks in the audio, right? I can use a helper called smooth value. You find it in the namespace standard smoothing. So if I say standard smoothing, smooth value, and I call it the smooth carrier frequency like this. I will use this struct to smooth my carrier frequency whenever I receive an input event of the carrier frequency. So when I have an event called carrier frequency, and the value which I get is a float, and it's the value, then I will need to define like what is the target, where should this smooth value ramp to. This is a bit of a calculation that is difficult to understand at first, so I will just show you in Max. We would like to smooth the input signal. So you see I have a rapidly changing input signal. But if I plug this directly to my synth carrier frequency, then I would get the clicks and the pops, right? So one thing I could do is to use this smooth value struct helper function that is built into CMajor. And what that will help me do is similar to this line object here in MaxMSP. So what you see is that I get a value. Now it's 0, now it's 1. And then the line is helping me to ramp to that value. So currently the line has an internal value of 1, but I set it to 0, and then it ramps over 1,000 milliseconds or 1 second to the new value. So now it has an internal value of 0, and now I set it to this number and it ramps over 1 second to this value. So this will help me smooth my input value to avoid getting the clicks and the pops from the oscillator when the carrier frequency changes. So the smooth value has a function called setTarget, which take a target value that would be which target value am I ramping to, but then we also need to tell it how many steps will it take for the smooth value to ramp to that target, and what does that mean exactly. Let's make an example where we would like to ramp from 0 to 1. First, we need to figure out how long it takes to calculate one sample. So if this is 1 second, and our current sample rate is 44,100 samples per second, or frames per second, then it takes this amount of time to calculate one sample. So this time unit is the same as one step. So one step is like, how many times do I need to add this number to itself to reach 1? How many times does the computer need to help me click this button to go from 0 to 1? You find this number by dividing 1 with this time unit and get the number of steps. If you adding this number to itself this many times or this many steps, then you get the number 1. A problem we are facing is that this division is resulting in a floating point, and it doesn't really make sense to define the number of steps as a floating point. So you will see we have to cast that to an int. So actually, when you add the number to itself many, many times, you don't exactly reach the target value. You reach something that is very close to. Luckily, they thought about this when implementing the struct smooth value. So you see from the CMajor documentation that when you use the function called getNext, which we will talk about in a bit, and there are no more remaining steps, then they will just return the target value. So actually this problem with the floating point division is not an actual problem when using the struct smooth value. We will use the struct and we will say setTarget. We want to reach the value, like we want to reach the carrier frequency, and we want to reach it by saying the amount of time to reach the target divided by the processor.period, which is a built-in constant of CMajor. The processor.period, it's the length in seconds of one frame for this processor. But you can see the processor.period is a float 64. So we need to cast this to a float. Now this division will most probably be a floating point value. So we will cast this to an int. But because this could potentially be 0, then we will also wrap it in a function called max, which returns the largest of these numbers. So if this is 0, then it will return 1. But if this is larger than 1, then it will return this one. That's the max. It is also defined here in the documentation. So now we have the steps to reach the target, and we have the target value. So now we just need to actually make the ramp. We need to press the button and see that it ramps. Like this, right? So a processor needs to process something. So it has a main function, and inside that it has a loop. This loop is advanced with one frame or one sample using the advance function. So every time the advance is called, it means like calculate the next frame. If you want to make the struct kind of like press this button and increment with one step, then we use the getNext function. And that is called getNext. And it is described getNext like this. So this returns the current value and increments it towards the current value. So if we want to see what is the next value, then we can use our new snippet. And then we will see the console output of the smooth carrier frequency. So you see it takes like 1 second to move to the next value. And it's quite laggy because I'm console logging all the values every single frame. I just realized that I used the name value as the input carrier frequency. That's maybe not the best idea because value is actually a keyword in CMajor. When you are defining endpoints, there's an endpoint type called value. So we should change that to say frequency maybe. So to create our own oscillator, we need to store the phase of the carrier frequency. So we will create a float for that, carrier phase. Okay, so what is the phase exactly, and how can we use it to make our sine oscillator? So this is the unit circle. Currently the phase is 0. It's this point over here. So if you think about this point as being the x value, then that's kind of a lookup for the y value, right? So the sine for the phase of 0 is a y value of 0. So if you increase the phase towards pi divided by 2, then the sine to the phase will be 1. If you increase the phase towards pi, then the sine to the phase will be 0. If you increase the phase to 1.5 pi, I don't know if that is the correct way of saying it, but then the sine for the phase will be -1. And if you make one full revolution towards 2 pi, then the sine to the phase will again be 0. So how does that look in something that looks like a DAW or like amplitude variations when we make techno music? Then I tried to make this animation. If we take a look at this circle again, you see there's the point on the circumference of the circle. It moves in the phase of 0 to 2 pi radians. And the resulting y value, if you draw it together with time, then that's kind of like the amplitude variations of your oscillator, right? So if you increase the frequency, then it basically just means that the phase will move more rapidly around the unit circle, which will result in more rapid amplitude variations like this, right? So we could just say that the audio out is the sine of the carrier phase. And maybe also just lower the volume. So we are taking the sine function of the phase, but we are never increasing the phase. It would mean that we're just in a constant value of 0. We don't have an oscillation like this or like this over here, right? So we need to increase the phase every time we advance one frame. So after we output the current value of the sine function to the phase, we want to increase it. So let's make a new constant for this loop that's called carrier phase delta. And delta just means what is the change of phase from here to here. That will be the phase delta. Okay, so we want to find the change of phase for the carrier oscillator. And the way to do that is that we need to have the input, the carrier frequency. We need this processor period, which was the process time per sample. We also talked about that earlier. And then we need 2 pi, because we saw earlier that 2 pi radians means like one full revolution of the unit circle. So let's say we have a carrier frequency of 1 hertz. That would mean that there's one full revolution per second. If we multiply these 3 numbers together, this is this expression in MSP, then we get this number. So this is the change of phase in radians per sample. And a quick check to see if we are correct is that we multiplied with the sample rate, the amount of samples per second. And we see that it's almost resulting to one full revolution. It's actually a bit more, and I'm not entirely sure why, but I suspect that there's something with the decimal range of pi, which is quite long. So maybe it's a bit wrong the way that I display them here. But anyway, this is the calculation. So let's try to do it in C major. So we needed the carrier frequency. We used the smooth carrier frequency, and we used the function called getNext, which returns the current value and increments the smoothing function if it's in the process of making a ramp. Then we multiply it with the processor.period, and we multiply it with 2 pi. So we need to add the phase delta to the carrier phase. So we say carrier phase. Yeah, we could do that. But the problem is that this number will be quite huge very quickly. So instead of doing it like this, we will just say carrier phase is the same as carrier phase plus carrier phase delta. And then we modulo it by 2 pi. Actually, there is a built-in function into CMajor, which is called add modulo 2 pi, which basically does the same thing, adding 2 floating points together and modulating with 2 pi. And you don't need to use the standard namespace because as described here, it's kind of as if this function was in the global namespace. So what we can do instead is just writing add modulo to pi, the carrier phase, and the carrier phase delta. So now we increment the carrier phase with the delta value for each revolution of the loop. Let's try it. It's because the carrier phase is float 32 and the processor period and maybe also 2 pi is float 64. So we need to cast this to a maybe we need to cast this to a float actually. Let's try that. Cool. So we have sound, and that light is quite explicit because the smoothing time is so long. So maybe we can just make the smoothing time like 20 milliseconds or something. 20 milliseconds. Okay, now I don't hear the steps. So that's cool. Maybe it's a bit long. All right. So next up is the modulator or the modulating oscillator.